In exercise 1212, we're trying to do another multi-step synthesis. And so the first step would be to see what these two molecules that we start with and that we end up with have in common. So if you look at the structure on the left, you'll see that there is a similar structure on the right, although it changes a little bit. And when you sort of visualize them in that way, you'll see that the number of carbons on the left and the right increases. You have that same piece that you had before, but then you have an extra carbon outside of that piece. And notice this includes that methyl group on the fourth carbon there. But you have 5 carbons in your if you want to think of it as a parent chain of your original molecule, those same 5 carbons are still there, but there's a 6th carbon attached. It's attached as an aldehyde. The aldehyde all by itself should make us suspicious. In the back of our mind, we know one way to make an aldehyde, and so I'll just write that as a sort of rough draft note. We have an aldehyde. That's a sign that we probably did ozonolysis. Ozonolysis with an alkene. And what made me think of that was the fact that we had an aldehyde here. Remember, an aldehyde is when you have a carbon double bonded to an oxygen and a hydrogen on one side of that. That's an aldehyde. Well, it's kind of strange that we see this sign of ozonolysis because the number of carbons increased. Oops. We went from having 5 to having 6. And we know that when the number of carbons increases, we have to do 2 things. We have to add an alkyl halide. That's one thing. To a terminal alkyne. A terminal alkyne that we mix with sodium amide so that it turns into a nucleophile. Now we've seen that several times before in this chapter, this process of adding carbons onto a chain. Now the question is, we need these 2 things to add this carbon on, but which should be the alkyl halide, which carbon chain should be the terminal alkyne? Should we turn this original carbon chain into a terminal alkyne? Or should we have a separate terminal alkyne and make this an alkyl halide? The sign for that, to decide that question, look at the product. Where is the most reactive part of that product? Notice that it's on the part of the molecule that is not contained in the original carbon skeleton. That means that you want to introduce a separate terminal alkyne. If the reactive part of the molecule is not on the original carbon chain, then you want it to be on the carbon chain that you introduce. Because if you need to create an aldehyde, then you're going to need extra electrons. You're going to need extra molecular glue to stick stuff on there. And that glue will come from the alkyne. So wherever you have a sort of functional group, that's where you want your alkyne to be. And we have our functional group on the part of the carbon chain that was not in the original structure. So we're going to add that aldehyde we're going to add that 6th carbon by adding this terminal alkyne. Our original molecule will be an alkyl halide. So we're going to turn this into an alkyl halide. And notice where we want the alkyl halide to be. We want the alkyl halide to be on carbon number 5. That's where, because we're making a new carbon-to-carbon bond between 5 and 6. So if this is the alkyl halide, the alkyl halide needs to, the halogen, the leaving group, needs to be on carbon number 5. So let's sort of make a draft of that. We know we need this to be an alkyl halide. The alkyl halide needs to be on carbon number 5. So we could draw that in. This is what we need. If we have this, then we could take this carbon 6 and bond it to it by doing an SN2 reaction. Okay, well, how can we get there? We have an alkene, so we can add something onto that. That's good. We see a bromine. We see a bromine, and really not much else. Although if you squint, you'll see a hydrogen next door to it. It's not written in, but it's implied. Notice that there's no hydrogen on this carbon above, but there is one on carbon number 4 below. So we added both a hydrogen and a bromine. So hydrohalogenation. The question is, how do we want them to add? Markovnikov or anti-Markovnikov? If you look at these two carbons, you'll see that the one that the hydrogen is on is bonded to 1, 2, 3 other carbons. So it is tertiary. The one that the bromine is on is only bonded to one other carbon, so it is primary. In other words, we want the hydrogen to go on to the more substituted carbon. That is anti-Markovnikov addition. So we want to add peroxides here, ROOR, in order to get that anti-Markovnikov addition. Well, once we have that halogen added, now we can introduce our terminal alkyne. And at this point, I think it's a good opportunity for me to point out another strategy that's very common in these synthesis questions. An important thing to remember. Don't wait until you see the whole answer to start. Start before you see the whole answer. Look for key pieces that suggest single steps. I see a pi bond, I know I can do an addition reaction. I see extra numbers of carbons, I know I have to use an alkyl halide and a terminal alkyne. Look for key structures that remind you of individual reactions, and then just try, even though you can't see where it will go, you don't know where it will go, try something out. If it works or if it doesn't work, either way you'll get information that will lead you to a better synthesis. So, don't wait until you can see the whole change in order to write anything down. Now here we have our alkyl halide, so we can introduce our alkyne. So if we put these numbers back in, we have 1, 2, 3, 4, 5. We can make this carbon a better nucleophile by adding one equivalent of sodium amide to it. That will rip one of the terminal hydrogens off, turn the electrons that were in the bond to the hydrogen into a lone pair, and that carbon now has a full negative charge. This is a process we've seen many times, which is why I'm not trying it out. We have bigger fish to fry here. So this nucleophile can come in, kick the leaving group off in a classic SN2 reaction. And what we have at this point is the same sort of molecule, but the nucleophile will replace the leaving group. So the bromine will be replaced by this triple bond. So now we have that carbon. Now we've come a long way. We've added a carbon, sure, but unfortunately we added too many. Now we have 7 carbons, and here we only have 6. And so we need to reduce the number of carbons. And so it's here where that first idea that we noticed, the presence of that aldehyde, which suggested ozonolysis, that comes back to us. Because ozonolysis takes a carbon off of the carbon chain. And that's what we need to do here. We have 7 carbons and we need 6. Now we can't do ozonolysis on this alkyne. If we do ozonolysis on this, if we treat this with ozone, and when you do it to an alkyne, the second step you add water. If you did that, then you'd get 2 pieces. First it would cleave this triple bond, and the 2 pieces would be, on carbon number 6, you would have a carboxylic acid, and the 7th carbon would have turned into carbon dioxide. That's what you get if you did ozonolysis there. That would give us a carboxylic acid, which is not what we want. We want an aldehyde. And so we know, like we knew before, we need to do the ozonolysis on an alkene. So first we have to turn this into an alkene. So we do a reduction. We know 2 ways to turn this into an alkene. We could either use bubble hydrogen gas through there with Lindlar's catalyst, or we could use dissolving metal reduction, so solid sodium and liquid ammonia. Either of those would give us an alkene. Now be careful, if it's possible to get a cis or trans alkene, Lindlar's catalyst would give you the cis alkene, and dissolving metal reduction would give you the trans alkene. But because this is at the end of a chain, you can't get cis or trans with this, and so because there's not a carbon chain on both sides. And so here, either of these would just take us to the alkene. You have to be a little careful, just as a side note, in terms of practicality, when you do these reactions, you have to be a little careful, because if you run them for too long, they'll end up taking you all the way to the alkane. But that's a practical side note. Here, we'll assume you do them in the right amount of time, and so we'll change this into an alkene. So we have our 7 carbons in our alkene now. And once we have our alkene, now we can do the ozonolysis. Now remember, with an ozonolysis, you want to always add ozone, but if you're doing it with an alkene, the second step is DMS, dimethyl sulfide, so sulfur with 2 methyl groups on it. That's going to act as your reducing agent here. That will cleave this bond and give us aldehydes or ketones. So here, we'll have our 6 carbons. On the 6th one, we'll have the double bond to the oxygen, and then we have that one other carbon that ends up being the smallest aldehyde, formaldehyde. That's not part of our story. That's for us, that's waste. Maybe that goes on to live a different saga and be the hero in a different story, but in this story, we're interested in this carbon chain. That carbon chain is our final product. So if we take that back up here and compare it, that is the same thing as this. Now, it may not look immediately 100% the same. That's because this single bond can rotate. If you rotate this around, you end up getting this. Notice that structurally it's the same. You have 6 carbons, a methyl group on carbon 4, and an aldehyde on carbon 6. So the same thing. Okay, so we noticed a couple things here. We noticed that we had more carbons in the product than we had in the reactants, and that was a sign that we had to use an alkyl halide and a terminal alkyne. The fact that the more reactive thing, the functional group, was on the carbon that was not in our original chain was a sign that we wanted the terminal alkyne to be the carbon chain we added, and we want the carbon chain we start with to be the alkyl halide. So we did anti-Markovnikov addition of HBr. To get the halogen, the leaving group on carbon 5, we took ethyne, treated it with sodium amide to make a nucleophile out of it, did the SN2 reaction, and added our carbons. But then we stood back and we noticed we added too many. We had 7 and we wanted 6. So now we had to remove carbons. And that was a sign that we should use ozonolysis. We had a hint of that from the very beginning because we saw an aldehyde. That is a key structure that would remind you of the ozonolysis of an alkene. We couldn't do the ozonolysis on an alkyne because it would give us carbon dioxide and a carboxylic acid. So instead we reduced this, we added hydrogens onto that to get an alkene using either H2 and Lindlar's catalyst or solid sodium and liquid ammonia. Lindlar's catalyst would give you a cis alkene. Dissolving metal reduction would give you a trans alkene. Here, because it's at the end of a chain, you can't have cis or trans, so either would work. And once you have the alkene, we did ozonolysis in 2 steps. We bubble ozone gas through and follow it up with dimethyl sulfide, DMS, and that gives us our aldehyde, in addition to formaldehyde somewhere else in the room, or somewhere else in the container, the beaker. So overall, if somebody wanted to make this transformation happen, the recipe you would write out for them is first treat your alkene with HBr in the presence of peroxides. Then take ethyne and treat it with sodium amide, one equivalent. That will turn this into a nucleophile that will attack the alkyl halide you made in the previous step. That gives you your carbon skeleton. Then you have to reduce it, let's use dissolving metal reduction, solid sodium in liquid ammonia. And once you have that alkene, you just do the ozonolysis to remove that one end carbon. That's a two-step procedure. When you're doing ozonolysis on an alkene, the first step is adding bubbling ozone gas through there, and the second step is treating it with some dimethyl sulfide. So overall, this recipe would accomplish this beautiful transformation.